Welcome back to Stage 1 Mathematics Growth and Decay. In this video, we're going to look at exponentials, but rather than looking at exponentials as simply equations, we're going to look at them in the form of functions. So consider the simplest form for the exponential function can be written as y equals a to the power of x, where a is greater than 0, and it can also not equal 1. Now, if we wanted to visualize this particular function, y equals a to the power of x, then what we can do is we can first plot the values in a table, and then we can plot these points on a graph and then look at the shape. So starting from 0 and going to our positive numbers or positive values of x, we'll start off with 2 to the power of 0. And we simply know that's going to be equal to 1 because anything to the power of 0, with exception to 0, of course, is going to be 1. Then 2 to the power of 1 is simply the base itself, which is 2. 2 to the power of 2 is going to be 2 times 2, which is 4. And 2 to the power of 3 is 4 times 2, or 2 times 2 times 2, which is 8. Now looking at our negative numbers, we're going to get 2 to the negative 1, which is the same as writing 1 over the base, which is 2, or 0.5. Next one, 2 to the power of negative 2 is the same as writing 1 over 2 to the power of 2, or 2 squared, which is simply 4. And 2 to the power of negative 3, that's going to be 1 over 8. So as you can see, starting from 0 and going positive, our numbers are growing at an increasing rate. And going from 0 into the negatives, our values for y are decreasing at they're getting smaller at a lower rate. So if we plot this on our Cartesian plane, so first labeling our x, and we'll say that's the positive direction, and our y with the positive direction here. If I plot all the points, we can see that when x is 0, y is going to be 1, like so. And when x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. Now, if we tried to plot when x is 4, then we'd be off our Cartesian plane here, so we won't bother plotting that one. Now, going across into the negatives, when x is negative 1, notice the value of y is a half. For negative 2, it's a quarter, and for negative 3, it's an eighth. So, getting my very thin purple pen here, if I draw a curve that passes through all of these points, notice the shape that it is carving out. So for positive values, it grows quite rapidly, and for negative values, it tapers off and tries to approach the x-axis, but never quite gets there. So what we can see here is this is our graph for y equals 2 to the power of x. So there are a few properties that we can say about this particular function here. And the first one we can say is, notice the y-intercept. So when x is 0, y is 1. So for this particular function, y equals 2 to the x, we can say passes through the point 0, 1. Now the second point we can mention is y equals 2 to the x is always positive. So look at the values for this function. At no point does it ever go below the x-axis, and therefore for all values of x, we're going to expect to see positive values for y. So we can say y to the x, y equals 2 to the x is always positive, so above the x-axis. Secondly, this goes on from what we just mentioned about the positivity, but notice for negative values of x, the value of y decreases ever so slightly towards the value of 0. However, it never actually touches the value of 0. So there is no value for x that you can put into this function here that will ever give you a value of 0 for y. But the numbers themselves are heading towards 0. So what we can say is that there is an asymptote at y equals 0. So we can say is asymptotic. The third point we can mention about this is notice that for this particular function, there's no real turning point. So it doesn't simply go from positive to negative because it just doesn't happen. So there's no turning point for this function, and therefore there are no points of inflection. So like something sort of whipping like that. There is none of that going on in this function. So we can say has no turning points nor inflections. Has no turning points nor inflections. Fifthly, we can see from low values of x, as x increases, so does y. So it is always increasing. And we can also say it is always concave. So we'll leave it there for this video, and in the next video, we'll have a look at the general exponential function.